So we're going to be talking about isotopes and average atomic mass today. An isotope have the same number of protons but different numbers of neutrons. And if they have the same number of protons, they have to be the same element. So the only thing that's going to be different is our mass number. You're going to be asked to write things in hyphen notation on some of your worksheets, quizzes, and tests. To do so, you just write the element name and then the mass number. This distinguishes different isotopes. So here we have 3 isotopes of hydrogen. We could write hydrogen-1 for our first isotope, or sometimes you'll just see it with the symbol and the mass number, as in H2 and H3. Looking at that first picture of hydrogen, notice it has 1 proton and no neutrons in the nucleus. The second hydrogen, we have 1 proton and 1 neutron, and in hydrogen 3 we have 1 proton and 2 neutrons. Notice the protons stayed the same, because if you change the number of protons, you're going to change the element. So the only thing that differs is our neutrons. Here you can see helium has 2 isotopes, helium-3 and helium-4. Helium-3 has 2 protons and 1 neutron, while helium-2 or helium-4 has 2 protons and 2 neutrons. Again, our protons stayed the same. For the 2 isotopes of lithium, lithium-6 and 7, they both have 3 protons, but lithium-6 has 3 neutrons while lithium-7 has 4. Isotopes has nothing to do with the electrons. It's only affecting the neutrons. Go ahead and pause the video and solve these 2 on your own. Restart when you have your answer. So remember that that's our mass number, which is protons plus neutrons. For carbon, that tells us our atomic number has to be 6 because carbon always has an atomic number of 6, which means our protons are 6 and our neutrons are 6 because mass minus protons gives me neutrons. For the second example, it's still carbon, so it still has to be 6 protons. But mass minus atomic number gives me 8 neutrons. Another way besides hyphen notation is isotopic notation. It's another way of displaying atoms with lots of information. We have the mass on top, or the mass number on top, the atomic number on bottom, and then the symbol of the element, such as uranium-236. The bottom number is our number of protons, which is our atomic number. Mass is protons plus neutrons. So to find my neutrons, I would just subtract mass from atomic number. And you can figure out your symbol from your number of protons, which is our atomic number. Looking at the first example, we have 5 protons, 6 neutrons, and 5 electrons. If you have 5 protons, that's the atomic number. Looking on your periodic table, 5 protons, or atomic number of 5, represents the element boron. To get my mass number, I add my protons plus neutrons, which gives me a mass of 11. The protons and electrons are equal, meaning that this is a neutral atom. Go ahead and pause the video and try the next one on your own. Restart when you have your answer. So our mass number is 17, so that goes on top. Remember that mass number is protons plus neutrons, so since we know our neutrons are 8, and protons plus 8 has to give me 17, then I can figure out my protons. I get 9 for my protons, and looking at your periodic table, you should have gotten that 9 corresponds to the element fluorine. On the periodic table is the average atomic mass. It's a weighted average of the masses of all the isotopes of a particular element. So to calculate the average atomic mass, we would take the mass of the first isotope and multiply it by its percent abundance, plus the mass of isotope 2 times its percent, and so on, for all of the isotopes. For your percent abundance, make sure to change the percent to decimal form. So if I had 80%, I would need to change that to 0.80. To do so, just move the decimal over 2 places or divide by 100. Your average atomic mass should be between the mass of your lowest and highest isotope. If they're not, you've done something wrong. And again, this is what's located on the periodic table. So for this first example, we have chlorine 35, and they told us the percent is 75.53%, and chlorine 37, which has a percent of 24.47%. So I take the mass and multiply it by 0.7553. Again, I just divided by 100. And then added it to 37 times 0.2447. Before even plugging it in the calculator, I know my answer has to be between 35 and 37. If it's not, I need to recalculate. I get 35.4894. Since I had 4 sig figs in my percent, I'm going to go ahead and put my answer in 4 significant figures. So 35.49. The units for average atomic mass is AMU, or atomic mass unit. Make sure that you put your unit on your answer. Okay, go ahead and pause the video and try solving this one on your own. So here we have 3 isotopes with the percents of 90.92, 0.25, and 8.83. For your second isotope, make sure that you also divide the percent by 100. A lot of people miss this problem because they just see that it's already a decimal and so they don't divide by 100. You have to divide by 100 because all your decimals have to add up to 1, just as a percent would add up to 100. Again, my answer should be between 19.99 and 21.99, and it is, so I'm good. And just as before, I had my masses and my masses are in 4 significant figures. So 20.17 AMU. Go ahead and pause the video and try this one on your own. Restart when you have your answer. So here we have 2 isotopes of silver, 107 and 109. On the periodic table, the average atomic mass is 107.87. If they were 50% abundant of each of them, then I would have an average atomic mass of 108. But it's closer to 107, meaning that my weight of 107 must be more than 50%. So 107 is more abundant. When you have just 2 isotopes, the average atomic mass is going to be closer to the more abundant one. Again, had it been 50% of each, it would have been an average atomic mass of 108. If it was more than 108, then 109 would have been more abundant. Go ahead and pause the video and try this one on your own. Restart when you have an answer. So in this problem, you could have just looked at the problem and eliminated B, D, and E because our answer has to be between 13 and 15. A is exactly 14, so that's also not very likely, considering that we have 3 isotopes. Solving it all out, you get 14.1. So how exactly do we know the isotopes of elements and their masses? The answer is a mass spectrometer. In a mass spectrometer, an ion beam is shot from a source. It goes through a magnet. The lighter molecules come off first, and the heavier molecules or atoms come off later. And so we'll get the 3 isotopes, or 4 isotopes, or however many isotopes. Here we have a graph of what it would look like on the printout. Each spike is a different isotope. The higher the spike, the more abundant it is. So in this sample we have 3 isotopes, 20, 21, and 22. And these are our percent abundances, 90.7, 0.3, and 9. So use the average atomic mass, or calculate the average atomic mass using the graph to the right. We would do 20 times 0.907 plus 21 times 0.003 plus 22 times 0.09. And that will give you your answer of 20.18 AMU. So it's the same information and same calculation, it's just in a graph form instead of just given to you. Here's the other type of mass spectrometer graph that you'll need to be able to read. In this one, we have 5 isotopes, and the numbers on top do not add up to 100. Those are not the percents, but the actual number of particles. So step 1 is calculate the percent abundance for each isotope. So we have to add up all the particles to find out how many we have. And we have 200. So if we know we have 200, we can calculate our percents by just dividing the number of particles over 200. To calculate the actual percent, we have to multiply by 100. So isotope 176 has a percent abundance of 5%. (177) has a percent abundance of 19%. Go ahead and pause the video and get your other 3% on your own. Restart when you have them. So we have 27%, 14%, and 35%. Step 2, now we can calculate the average atomic mass for this element. So we know our mass and we know its percent. So 176 times 0.05 plus 177 times 0.19, and so on. So after plugging that in the calculator, I get 178.55 AMU. For step 3, to find out what element it is, the element closest to this would be hafnium, number 72.